Last video. I'll try and make this one quick so you guys have plenty of time to work through the lecture review and so on and so forth. So, geology. This is a study of Earth's physical features, process, and history. How the Earth was formed. In geology, there are 5 interacting subsystems, although this kind of spans beyond geology as well. Most of the time in geology, we're talking about the lithosphere. This is the uppermost mantle and the crust of the Earth. That's obviously the most active region in terms of shaping the landforms we see around us. The hydrosphere, that's all the water, the atmosphere, the air. The biosphere, all the parts of the Earth where life exists. And finally, the anthroposphere. This is the portion of Earth where humans exist and the affected portions of Earth by humans. So we're going to focus on the lithosphere. This is the uppermost mantle and the crust of the Earth. So if you took this big cross section out of the Earth, you would see that you have the core, and here we have both the inner and outer core. The inner core is actually solid just because of all the pressure that it's under. And then the outer core, there is some solid and some liquid. But really, we're talking about the mantle, and this is a lot of molten rock, and it says convective, and that's because there are convection currents. There are big channels of molten rock, some that's hotter than others, that moves around in that mantle. And on top of the mantle, there are big continental plates, and they float on these convection currents, and that's the crust that we're talking about. Those big plates are the crust. If you've ever learned about tectonic plates or the theory of plate tectonics, then you know that most of the land we see sits atop big pieces of rock, and these big pieces of rock are those tectonic plates. These plates fit together, but they're also sliding underneath one another or slamming into each other, buckling, crunching, and generating intense heat and pressure, which is what leads to a lot of volcanism. So we can see here we've got the North American plate, and there's smaller plates within these plates as well. The South American plate, the African plate, Eurasian plate, so on and so forth. The theory of plate tectonics was actually first conceived by a man named Alfred Wegener, and he kind of looked at the map of the world and saw, well, hey, it looks kind of like South America. It kind of fits right in here with Africa. And then if you took this big chunk of Eurasia and Africa, it kind of fit in here as well. And so he thought, well, maybe these plates used to all be connected, or these continental plates used to all be connected. And now we know that he was correct. So this mid-Atlantic ridge here is a big mid-ocean mountain range, and it's actually the site of 2 plates moving apart from each other. That's why there's a space between these 2 lines. So these 2 plates, the Caribbean, South American, and the African and Eurasian plate, these are all moving apart from one another. As they move apart, molten rock bubbles up to the surface, solidifies, and you have a big mountain range in the center. So I mentioned some of these plate boundaries, but I didn't really go into much detail. So let's do that real quick. So depending on the type of boundary, you're going to have different landforms forming it. I mentioned the San Andreas Fault. This is a lateral motion or strike-slip fault, sometimes even called transform fault boundaries. This is where 2 plates are moving past each other. The San Andreas Fault happens to be a right lateral motion fault. So if you were standing on the North American plate and you had millions of years to kill, you could watch the Pacific plate move to your right. It's because the Pacific plate is moving north. So eventually, where LA is now, it'll be hundreds of miles north of where it currently is. That's a lateral motion fault. This often results in lots of earthquakes, but never very many of large magnitude. Divergent motion faults, this is where 2 plates are moving apart, and so magma is going to boil up to the top and is going to form new crust as it reaches the surface. And this is what's happening in the mid-Atlantic ridge. And finally, convergent motion. This is where two plates are coming together, and you can get really intense earthquakes with these types of faults. Sometimes they'll just run into each other and buckle. Other times you'll have one diving underneath the other. So this plate is going to catch on this plate that's diving underneath. You're going to have sediment building up. Sometimes you'll have lots of tension, and when that tension is released, you get really big earthquakes. Additionally, you can get lots of volcanism at these convergent motion or convergent plates. As this plate dives underneath, there's lots of friction and lots of heat being generated. That's going to melt magma. This molten rock is going to float to the surface, and the result is volcanism. This here is the ring of fire. The ring of fire, right? So most of these are convergent boundaries where two plates are coming together. We also have some strike slip. The San Andreas Fault is obviously right through here. These volcanoes here are all part of the Cascade Range, and this is a convergent boundary where the Juan de Fuca plate is diving underneath the North American plate. Mount Lassen is one of the mountains in California that's part of that Cascade Range, as is Mount Shasta. Japan actually lies on a convergent boundary of 4 different plates. So there's lots of volcanoes and earthquakes that happen there. In fact, the earthquake that caused the Tohoku earthquake and the destruction of the Fukushima Daiichi nuclear power plant a few years ago, that earthquake occurred right here. That was a huge tsunami. So all of these red triangles are volcanoes that are part of a tectonic plate boundary. Let's zoom in now a little bit and talk about rocks specifically. So minerals and rocks are actually different things. A mineral is a more pure substance, if you will, that has a distinct or specific chemical composition and structure. So like quartz, for example. Whereas a rock is a combination of different minerals, typically. So you can think of concrete as analogous to a rock rather than a mineral. So how do these different types of rocks form? This is where the rock cycle comes in. So this takes place over hundreds of millions of years in some cases, where you have heating, melting, cooling, breaking, and reassembling of rocks and minerals. Sometimes rocks will form really quickly. And in the case of a volcano, right, a volcano erupts, magma is spewed out onto the Earth's crust. Once that molten rock cools, you have a brand new rock, more or less. That type of rock is called igneous rock. Some igneous rock is really old. So a lot of the rock in the Sierra Nevada is igneous rock. It's granite. And that granite was formed deep in the Earth's crust. As it cooled, it solidified and formed this igneous rock. Another type of rock, sedimentary rock, is formed when igneous rock, or even metamorphic rock, which I'll talk about in a second, is weathered. So you get like sand and silt and clay, which is just very small rock particles, being washed out, for example. And those are deposited in the bottom of a lake or the bottom of a stream. When that water body dries up, what's left is the sediment. Given enough time, that sediment will harden and become a sedimentary rock. Right? We call that process lithification. Finally, you got metamorphic rock. So you can take an igneous rock or a sedimentary rock, or both. And if those are next to one another, given enough heat and pressure, you can fold and bend and change that rock into a new type of rock called metamorphic rock. So good example of igneous rock, granite. Sedimentary, you can think of sandstone, and then metamorphic, gneiss, G-N-E-I-S-S. Here's some examples there. So here's Half Dome at Yosemite, great example of an igneous rock. Specifically, it's called intrusive because this rock formed as it kind of pushed its way into the Earth's crust and solidified there, and now it's exposed due to erosion, whereas extrusive igneous rock is formed whenever volcanic activity or magma literally spews out onto the surface and solidifies there. Here's some metamorphic rock, nice, in Utah. You can see the different layers, the folding and bending that occurred to make this rock. And then here's sandstone in Arizona, where you can see the distinct layers of sediment.